So in this talk, I want to tell you a bit philosophy, as I told you. So what are we doing? We are here, AiiDA is a general tool, but we will in particular use it for atomistic simulations. And the aim, the final aim of, I think, probably everybody of you in the research is really to discover new materials properties. And the question we want to answer with AiiDA is which tools are useful to help you doing this process. And as you might have guessed from the title of the tutorial, this is really focused on high throughput. And the reason why high throughput and in the field of first principle simulation has become very popular, I think, is due to two main factors. So already maybe you know this paper of a couple of years ago, where basically they took the 100 papers which received most citation ever in the whole scientific literature, including things we got a Nobel Prize, microscopes, etc. And the 12 among the top 100 were about DFT or DFT-related methods. And I think this is already very relevant. Maybe citation is not necessarily the perfect parameter to evaluate the importance of a field, but still, it means it really had a lot of effect, of impact. And this has been due also to two main factors. On one side, we have a lot of codes, many of them are even open source, which are very accurate and predictive in computing the properties of materials. On the other side, you know that there is this Moore law, which is still valid for top supercomputers. This, for instance, is a plot over time. This is from 1993 to 2013 of the throughput of top supercomputers in the world. The red line is the #1 supercomputer in the world, which of course stays often there for a few years, so you see these flat areas. But if you take the number 500 in the list, or the sum of the throughput of the first 500 computers, you see there is this, in this semi-logarithmic plot, you have this trend. So it's an exponential growth of the power, which, just to give an estimate, if a calculation would have taken 1 month in 93, with a perfect scaling, now it would take only 10 seconds in the top supercomputer in the world. Putting these two things together, you get the possibility to run high throughput design of materials. You have a lot of computation, a lot of very effective codes, and you can compute a lot of properties. The question we want to ask and then answer with AiiDA is really how to manage all the simulation. Because if you have running them, you know that you can easily get to run tens of thousands, if not more, computations. And when you have to go back and look for the results, you need to know an effective way to find what you've computed. And to make a comparison, if you go in a library and want to look for a book, you want to find them well organized in shelves and not randomly displaced on the floor. But if you think to it, often if you go in on the hard drive of a person doing simulation, often the situation is more similar to this. You have a lot of folders with simulation running different times, maybe with different parameters. It's hard to find them. With AiiDA, we want to have a tool which helps you in organizing your research. And we think having a tool which is designed from the very beginning to do that is very powerful. Everybody, probably of you in this room, has their own scripts, maybe more or less advanced to do things. But we will see it's not just about automation. The automation part, having a script which submits things, it's very important, but it's one of the components of the full ecosystem. And so I want to discuss a bit how we design the platform to be. We started thinking a bit what we wanted the platform to help us achieving. And the first thing was reproducibility. I think everybody of you has had this experience. You go in a paper, you try to reproduce a computation of someone else, and it's very difficult to do it because people maybe don't cite all the numerical parameters. It's hard to explain in a paper all the technicalities of how to converge calculation, etc. And so you really want to have a way to make it super easy to know exactly what a person did and be able to reproduce the same calculation again. The second part is searchability, in the sense you want to be able to know if you or someone else already computed something in order to avoid to redo computations, and also to collect them in a clever, let's say, way to allow data mining of the results. The third bit is, in a sense, what we call reliability, meaning that you want these results to be, on one side, persisted in repositories, but also you want to have automated procedures which allow you to get a repository and automatically recompute properties without any human intervention to make sure that the results you have are converged, are valid, etc. So we really need, and we'll show later the importance of this in AiiDA, have tools to run basically what we call workflows, which automatically and without human intervention recompute properties. And finally, you want to be able to share results with the community, either with collaborators. While you're working, you might want to give, you start with a part of the project, but then you ask someone else to continue. Or at the end, once you publish your results, you might want to publish them on an open source online repository, for instance. And having a tool which helps you, already the very fact of having things organized will facilitate you. But we think it's really essential to have these features because this will boost research. Because people often do research, but you don't have the time maybe to find all the information you have in a lot of data. And other people can just use it to discover new relationships, new properties of the materials. So what we did, we took these ideas, which were a bit like brainstorm, and then we put them in a more consistent environment, which we call the AiiDA model, AiiDA from automation, data, environment, and sharing, which are really the 4 pillars which we based AiiDA upon. There are 2, so automation, we are describing now each of one briefly. Automation, data, environment, and sharing. The 2 automation and data are really more low level, are more like informatics based, how to automate computations, how to store them, query for them, etc. The 2 on the right, environment and sharing, are more about how the user interacts with the platform. You will find information in this paper, which describes more in detail all the idea behind it, but in a few slides I will start describing AiiDA and how each of these pillars is implemented into AiiDA. This is just to give a brief overview for those of you maybe who are not yet using AiiDA. We started the actual development in 2012 with the first commits after early developments by Boris Koziski, who is one of the authors of AiiDA, who's a lead researcher in Bosch in the US. And then we took a few years to get to the first version, but then we had periodic releases. The current one is 0.81, and the version we use during this tutorial is 0.90 RC2, so it's a release candidate, which is basically ready. We will release the official version probably 1 week after the tutorial. But let's say the idea is that we're really having steady versions, and even if they're named 0 point something, they're really already stable and people are using them for real research. And we probably were thinking to have a short talk by Nicolas Mounet during the 3rd day, just to show an example of how AiiDA is being used currently in a practical research. And we already had 7 tutorials. This is the 8th one, I think. So really push a lot on really knowledge transfer and teaching how the platform works. The code is fully open source, has an MIT license, and is on GitHub, as you maybe already know. And you can get all information on our website. So what is AiiDA? So now I start speaking a bit more about AiiDA, about how it works. AiiDA is a software that you can think sits between you, the researchers, and the computers where you run your simulations, supercomputers or clusters or anything where you run your simulations. In between, you have a tool which often will sit and will be running on your workstation, for instance, in your office. And the idea is that it's really in between. With AiiDA, you don't need anymore to connect directly to the cluster, but you instruct AiiDA on what you want to do, and AiiDA will take care of interacting with the cluster. There are a few components of AiiDA which are very schematically represented here. The core part that we learned how to interact with already during this morning is the AiiDA Python API. So AiiDA is a Python code, and to use most of its potentiality and the functionality, you will use directly Python to interact with these classes. These classes map and, if you want, hide interaction with the database. So you will interact mainly with the ORM, which stands for Object Relational Mapper, which means basically that you have Python classes which represent what is stored, we map to the relations in the database. And the 2 main entities are calculation and data. You will also learn about codes. And everything is, first of all, as plugins, and we'll discuss this later, but it's stored in a storage which is composed of 2 main parts. On one side, you have the database, which allows you to make a very efficient queries when you want to look for results. And then you also have, alongside with this, a file repository. So big files are stored just as files, because very often you don't need to query for the 7th component of a charge density matrix. You just need to know the information. While for other things you need to query, you want to know if a structure contains silicon, or you want to know if a calculation was run with a given number of CPUs, etc. So this part is pretty transparent. You won't recognize it much, the division, just to know how it works behind the scenes. All the automation part, all the interaction with supercomputers, managing of workflow, etc., is managed by a component which is called a daemon, which takes care of submission, retrieval, etc. And I will mention one thing more in a couple of slides. And this interacts through different channels to the supercomputer. Most often will be SSH, but you can also install AiiDA directly on the supercomputer, for instance, and then you don't need to SSH. And AiiDA takes care of interacting with different schedulers, and we already have plugins for a number of them. And on your side, let's say on the way you interact with AiiDA, as I told you, most of it will happen through the Python interface. So you can either write through the basic IPython for interactive scripts. And you will see also with Jupyter. So if you don't know, we'll see what it is. Jupyter is a graphical interface through the web browser to interact with Python. A bit like if you have used Mathematica, the software, it's a bit the same idea. You can directly write Python scripts, so you can just write them and run them. Or there is a command line tool, which we'll learn about very quickly, which is called Verdi, which allows you to basically already ask AiiDA most of the questions you want to ask, which calculation are running, which groups I have, etc., through the command line. And we are working also on a web interface, actually, which I'll mention later. And maybe we have a short demo of what we call the Materials Cloud, which is a web interface to interact with the data. So let me now go through the 4 pillars, and I try to tell you why we implemented things in a certain way. So the first one is automation, which means really being able to run high-throughput simulations on a remote computer. As I told you, there is nothing new. I mean, everybody of you, I'm sure, has some scripts, Bash, Awk, PAR, maybe even Python or Perl. It takes your information and converts them to input files and send them. So that's, I mean, something AiiDA already does. And the reason we implemented into AiiDA is really to decouple it and avoid it. If you do a different project, you have to rewrite those scripts, because often those are fine-tuned. But the critical part, really, from a design point of view, is the coupling of automation and data. The idea is really the following. So you never directly interact with the supercomputer. You first write everything you want to do into the storage through Python calls, and we'll see how it works. And then the daemon will just go in the storage and look for the information and create input files and run them. This means that you are forced, basically implicitly forced, of writing everything first in the storage. Because this piece of code, without any interaction with you, will know exactly how to create the input file and how to run the simulations. This means 2 things. One, you have full reproducibility of the single calculations, because you know exactly which code you use, on which machine it sits, which parameters you use, which pseudopotentials. All the numerical parameters have to be stored before. And also, everything will be stored in a very uniform way, so it will be very easy later to look for specific input files satisfying some requirements. For instance, you want to get all calculation with a given cutoff, etc. But really, this coupling is essential, and it's one of the design cornerstones of AiiDA. Then there is the automation part. As I mentioned, there is a daemon. The idea is that when you submit a calculation, it goes through different states in the database. So anytime you can ask AiiDA, what's the state of my calculation? When you submit it, it gets flagged as a to be submitted calculation. Then it goes to the scheduler. AiiDA checks if the calculation is finished and then gets retrieved, parsed. The parsed results get automatically stored in the database. So as soon as the calculation finishes, you can already query for calculation matching some results. And then the calculation either finishes or might fail some cases, or you can also have a failed state. And as I was telling, you have already your scripts, but what we really try to push is really to abstract the API, so the way you interact with AiiDA, in a way which is fully independent of the problem you're trying to solve, of the code you're using, or the supercomputer you're using, if it's SSH, local, or the scheduler. So the idea, if you write something roughly like this, we will see in a couple of hours, where you basically say, run a calculation for 1 hour on 2 cores with this file and these parameters, and then you run it. If you just want to change computer, maybe even with a different scheduler, you just change here the name, and you submit again. And that's the only place we have to change information. And AiiDA will take care of converting the input to the different scheduler, etc. So really, the idea is that if you change completely project, change code, you still can use the same API. That's really something we wanted to push. So about automation, I think that's enough. Let's go to the second pillar, that is data. And it's a bit important because we spent a lot of time trying to figure out how to represent what one does every day in a computer. And the main thing we realized very quickly, and if you think to it, I think it's true for anybody in your research. I was speaking about reproducibility of single calculations. So by storing things in AiiDA, since the daemon has to read the inputs, you have to store all inputs, so you automatically get reproducibility of single calculations. But now if you think to it, if you publish a paper, it's basically, I think, never happens that you run one step for a lot of time. For different structures, you run one step of calculation, then you take the output and you publish it. You always have to go through many steps, conversion of structures, running multiple convergence steps, then doing some post-processing, etc. So what really matters from a reproducibility point of view for scientific research is really the full flow of what you've been doing from the very beginning, when you started, to the very final plot you publish. And so you don't want just to store the calculations, you want to store how these calculations are connected together. And how can you do it? So we took inspiration from what is called the open provenance model. And the idea is, in the end, pretty simple. You can think there are two types of entities, which we call nodes, and we'll see why in a moment: data and calculations. Calculations can be thought as black boxes, which take inputs data and produce other type of data in output. For instance, let's say this is a quantum espresso relaxation calculation. You have some parameters, maybe k points, etc., and you have an initial crystal structure. This is your quantum espresso calculation, and at the end, you have some converged parameters, forces, etc., total energy, and a relaxed structure. Now, the other bit is that once you have the relaxed structure, this can become an input for the next calculation. And so you can immediately see that this becomes a graph, which might look like this, where you start from a structure, you can relax it with some parameters, get some results in a new structure. And this can be, for instance, used to get a distance between two structures, but also used to do an SCF with other parameters and get final results. This, you see, is a directed acyclic graph because you go from inputs to outputs through the calculation. Acyclic because this is really the creation graph, and you cannot have as input something which you created. And if you think a bit to it, we think that by storing things in this way, and this is really the crucial part of it, we'll spend also some time about the provenance. It's what is called the provenance of the data. So knowing how it was generated at each step and which parameters you used. By storing things in a graph, the provenance is automatically preserved. So if you look at this graph, you already know, let's say you publish some total energy, you already know exactly where you started from, which parameters you used to converge, etc. So hoping that I maybe convince you that storing things in a graph is really the way to store a provenance, and therefore ensure provenance, reproducibility not only of single calculations, but of the whole workflow if you want. The next question is more technical: how we store a graph on a computer and how we can query it and ask questions. And so I just have one slide. I won't go too much in the details, but during the tutorial, if you have more technical questions, we are very happy to answer any question you have. The idea is that you want to store somewhere, in our case in a SQL database, that's a choice we made after doing a lot of benchmarks, nodes and links. These are the two main things we want to store. And for each node, you typically want to store also a lot of key value attributes. So for a calculation, you might want to store number of nodes 7, memory 2 GB per core, etc. Wall time is this. But for a structure, you want to store the coordinates of the atoms. For results, you might want to store energies, and so arrays, etc. So each node has a way to store a flexible number of attributes, key value, anything you want, integer, strings, and you can query for them. All the rest sits in this schema. This is a very simplified version. You have nodes, links, these attributes which live, so you can store any key value pair. Big files are stored, as I was mentioning before, just as files and not as in the database. And then you have other tables like the computers, the users, you can put comments, you have logs, etc. But having such a structure will allow you to really make very efficient query. We'll see tomorrow, I think, how to make queries. The other thing we did was really to decouple AiiDA from the actual backend. I will mention later the work. I want just to tell you a bit the story of the last year and what will happen in the next year, so you have an idea of what we are doing now. So this is really decoupled. We have multiple ways to connect to databases, and potentially, if one decides to really implement not in SQL but in a different database format, it's just a matter of implementing the right classes. But AiiDA is already decoupled from the actual backend. Now, I mentioned a bit the low-level ones. Let's see about the more user-level ones. And the first one is environment. So with environment, it means really, if you want, is AiiDA easy to use, and how can we make your life easier, your research more effective? And these are a number of points. The first one is really how, so environment in the sense, creating a research environment for you, how you interact with it. So as already told, this is a Python code, so it's a quite high-level code. I think everybody of you already knows at some level Python. Anyway, it's very easy to learn, so it's becoming also a bit the standard in the community for post-processing. The other part is how to query. And as I told you, it's very important to have a database behind the hoods, because it allows you to ask questions and get very efficiently and quickly an answer. But you have to answer in some language. And every database has different languages. There is SQL, or if you use that for a database, there are different languages. But most of you probably don't care much about learning SQL. It's technical. And also, the way we organize data to make it more efficient makes the query a bit cumbersome. For this reason, we developed a tool that we will learn tomorrow morning, which is called the Query Builder, which allows you to write basically Python syntax and dictionaries and create queries which are automatically converted in SQL or whatever language there is behind. So you just have to say, I want a calculation, which is let's say a relationship to an output, and the output has an attribute called in this way with this parameter. So if you want this, again, it's on the user level. It makes it very easy to do queries. We try to make it as easy as possible to interact with it through the command line, through Python scripts, and we'll see also we're working a lot on this web interface. And we have a lot of documentation online at this address. We are doing tutorials like the one you are here today. And so we're trying to improve it all the time based on our experience of our colleagues, and the feedback you will give us at the end of the tutorial. So really, hopefully everything is explained already here, so any questions should be here. If it's not there, you can ask. There is a mailing list which is mentioned in the AiiDA website. So you are very suggested to register to it. It's very low traffic. It will be maybe one mail per week, so it's really low traffic. But you can ask things, and also you can be informed of new events, etc. But the other important thing is that really we designed AiiDA with modularity in mind. So we didn't want to have a tool which is specific to, say, Quantum Espresso for doing a specific type of calculations. We wanted something which was general for any code. So everything is done with plugins. We can have plugins for creating inputs, plugins to parse outputs, plugins to manage data types. So every data type has a specific type in AiiDA. You can have, for instance, crystal structures, which have a method to ask for position of atoms, volume of the cell. You have classes for pseudopotentials. You have classes for files. You have classes for band structures, etc. And these are also plugins, so you can also easily add new data types if you, for instance, you have a code which accepts a specific format. You have plugins for how to connect to the supercomputer, SSH, local, etc. For the schedulers, you have many of them. For importers from external databases, and for exporters, to some of them can also accept contributions. So you have all this, etc. So everything is really meant with plugin interface in mind. And if you want to add functionality, it's very easy, and actually you're very welcome to contribute to the development. But the essential part, really, probably that's the most important part, is really scientific workflows. So I already think stress enough the importance of keeping the connected structure. So to know when you get a final result, how you obtained it through maybe a complex network of calculations. But what I've been showing up to now is if you want a log of the past. So you run something, AiiDA stores it, and if you go back, you see exactly what you did. But what is most important is also to have a way to reproduce and run new calculations, generate new data. And so this is what the workflows are done. As I said, it's not just past, but also encoding how to generate new data. And the idea is really to create something which is, say, the word here is turnkey solutions. Like you go in a car, you just turn the key and the car starts. You don't need to know how the engine works, at which temperature the fuel will start to ignite. You really just want something, you give the basic information, like the crystal structure, and at the end you get the result. The person who develops the workflow, and that's a huge work. I mean, a research project at each of these workflows often, if you want to do something very complicated, it's really something big, but the researchers, one of you, can put all the knowledge you have, what you would do by hand, like checking if the calculation crashed, changing some parameters, choosing the right cutoffs. you put in a workflows, and other people can use it as a black box if you want. More depending on the type of project problem, sometimes it's possible, sometimes it's harder to do, but really allows two things. On one side, you can easily validate results. So let's say someone gives you a crystal structure and says this is the band structure, and it gives you 1 million. Well, maybe 1 million is a lot, but 10,000 of them, and you want to see if it's true. If you have a workflow, you just run one again. Maybe your parameters are converged, and you check if it's true. Or you can check. You can do verification. You can check different functions very easily. But also allows you to use components as black boxes for a bigger project. And we'll mention maybe later an example where this is very relevant to explain why this is important. But just to mention, we'll stress a lot, I think tomorrow afternoon, the importance of the provenance. So the only way to preserve what you have done is to make sure basically you have these links in the database. AiiDA tries to do as much as possible to make it transparent to you, but you have to put a bit of thought. For instance, here I make an example where I want to sum two numbers, multiply by a third number, and get the result. So this is clearly, I stated now, an example in which you don't want to store things at this level in the database. We don't expect you to store sums and multiplication in the database, but it's the simplest example just to show the idea. So you have some functions which, a function which does the sum, a function which does the product, and a function which does the final result. You pass some inputs, 3, 4, and 5, and you want to get the result. By just putting these decorators, these are called decorators, just putting @wf on top of the line defining the function in Python, what happens in the database is that everything gets stored. So there's just some beautification to convert numbers into AiiDA nodes, but let's say this creates 3 nodes, 3, 4, and 5. And this, you see, become parameters A, B, and C to this function. Okay? By just putting this, as soon as you run this gets stored in the database. You don't have to do anything. This will appear automatically in your database. This function by itself we call a function add. This would be add, sorry. And this is multiplication. So we call these two. There's a call link. Passing some parameters. So A and B go here. And the result is 7. Gets as an input A together with B. And you get the final result. So again, this is a very simplified example. We don't expect you to go at this level of provenance, but the idea is really to show the idea. You put just a simple decorator, and AiiDA takes care of storing nodes, links, and etc. for you. At the end, if you want to know how you obtain this number, you can go back and see exactly how it was called. Okay? So imagine now this for more complex things, where, for instance, one of these is taking a crystal structure, changing the volume to do an equation state. Actually, this will be an example tomorrow. This is very important, otherwise you will, if you don't connect, let's say, the initial structure to the relaxed one or the final one, you don't know how you created it. So having the AiiDA, so just by using this, we try to make it as simple as possible, creating these links. You have to remember to put this, so it's important to think about it. This is just one way to write workflows. There is a more advanced one we will learn tomorrow afternoon and Wednesday morning, I think, which has a lot of features. You can, as you saw, automatically track the provenance, but also run in parallel serial and parallel computations. You can checkpoint workflows and basically stop at some point. You can even turn off your computer while the calculation is running, turn it on later the next day and continue. You can reuse and nest the workflows, and you can, and this I will describe in the next slide why this is important. And the way you write workflows, you will see, basically it's an automatic documentation of the workflow itself, because you will be asked, it's optional, but basically very suggested to ask what are the potential inputs of a workflow and what are the steps you go through. And basically by just looking at this initial part, which is called the outline of the workflow, you see it and you understand more or less already. Even if you don't look at the code, you might understand what the workflow does. But I wanted to spend one more slide on this point, which is nesting and reuse. And here I have, okay, well, I'll, actually, sorry, it's the next slide, but before I want to show this. So the idea is these turnkey solutions. So turnkey solutions means really you pass a minimal input. For instance, here I want to do a phonon calculation. I just pass, a structure, a set of pseudopotentials I want to use, some computer, some basic parameters. I send this, and what happens in the database after maybe a few hours or days, depending on the structure, I get this in the database, which I zoom a bit just to show you. You have all the connections. You see, this is a calculation which have a number of inputs. They get an output and so on. And if you look here, I mean, when you don't know, it's a bit confusing maybe, but you start, you do a VC relax, so you relax the structure. Then you split the calculation over Q points. Over each Q point is run in this specific workflow on different nodes. Then you collect them, and then you do the final step of interpolating in real space, and then interpolating back in Fourier space to get the band structure. So, just as input generates all this for you, and you get the final result. But things can be much more complex. You might see something on Wednesday. On Wednesday, we see this short presentation. Just again, what I was mentioning before, a short example of how AiiDA has been already used in production to run hundreds of thousands of simulations and discover new properties. So I won't tell anything now because Nicola will present it. I just want to, actually, I think I missed a slide here. What I wanted to say about nesting, so I just tell it like this. Imagine you want to do phonons, okay? So you have to do a number of steps. You have first to do a relaxation. We will see some code. You need to do phonons, maybe interpolating on different Q points, etc. Now, at the lowest level, you typically want to have a workflow which takes care of managing your code. For instance, if it's quantum espresso, the code might crash for a number of reasons, and you might know already what to do to fix the problem. For instance, often the code crashes because the diagonalization scheme, by default, uses a very efficient one, the Davidson, but it's not so robust as CG. So you already know that if the code crashes with a specific error message, you want to restart it with a different algorithm, which doesn't change the result, but just converges. So at the low level, someone which is very experienced of the code can write this workflow. Now, this workflow can be given to someone else, which takes care of putting on top some logic to converge a calculation with multiple steps, for instance, until you really get the convergence with some cutoffs. Maybe you can start with loose parameters and then improve them. And then on top, this convergence workflow, if you want, can be put in a top-level workflow, which just calculates the phonons for you. And if you think at this point you have a phonon workflow, and if you want to compute very complex advanced properties, for instance, quasi-harmonic approximation to compute thermal properties, or follow unstable modes to find the stable structure, you don't need to worry anymore about how to write it. You don't need to worry how to compute, how to parallelize phonons, how to converge a calculation. Just take this phonon workflow as a black box, and you worry about the science. You worry about the real interesting part, which is using the phonons to do something else. So that's why we think having modular workflow is really essential and to really boost research. Okay. And of course, to do this, you have to share either the data or the workflows. So the first part is, of course, sharing the data. And from the very beginning, we thought about what would be the ideal way to share the data. And in the end, we decided not to have a center repository online where you log in, you have your data there. But by default, AiiDA works like this. You have your own computer with your own AiiDA instance. You have your data. And that's what you have. It's private. So you're also sure often, if you want to publish it, you are sure nobody can steal it. Or if you want to do a patent, it's private. But then with AiiDA, you have ways to share parts of the database, either with collaborators using AiiDA or directly with online repository. You can take structures, for instance, from COD, which is something you will see tomorrow, I think, do some computation and give them back to TCOD, which is collecting results, for instance, of crystal structure to other systems like Materials Cloud. So Materials Cloud is something we've been working for the past year. And I think on Wednesday, Fernando will show just 15 minutes a demo of what it is. And we'll be online probably at the end of September, even if some tools are already there. It's basically, if you want, it's a lot of things, and I don't want to present them now, but one of the things it does, if you know Git, how Git works, if you want, AiiDA works a bit like Git. It's something you have locally, you work with your data, and then if you want to publish it or share it, you put in for Git on GitHub, for AiiDA on Materials Cloud. You have a private, so you have an area where you can put your calculations, and people can look at them, understand how you computed them, but it's much more. It's not just this, and Fernando will mention something. And one of the things which is there is not just sharing the data, but sharing also the workflows, sharing the code. And for this, we are really pushing toward a kind of app store model where you can have apps, which in the end are just AiiDA plugins, where you have, for instance, already the plugins for parsing output of codes or creating inputs. You already have supercomputers which are pre-configured, so you can just take this and you already have the computer and the codes pre-configured. Or workflows. So for instance, you can have a workflow for transport, a workflow for phonons, one just to compute electronic density, one to compute optical properties. You can share your work with people if you want, and even maybe get cited for those. people can get them, use them as components of more complex workflows, and maybe share the more complex workflow again. Okay, so before, so you're maybe a few minutes later, just quickly, before going to the acknowledgements, I wanted to show you a bit, tell you what we have been doing the past year and a half, and tell you what will happen in the next months. So the first thing we did was to make AiiDA independent of the backend. So backend, I mean the database. So there are different implementations now, and if one thinks one wants to make it more efficient, one can easily implement a new one. But the main reason to do this was to use a new schema and a new way to connect to the database, which uses what are called JSON binary fields, which in practice for many important queries gives you up to 50 times speed up. So it was a really important change. The other thing we'll learn about tomorrow is implement a query builder, which is a tool to allow you to make easily, as I was mentioning before, to make easily queries without having to know anything about SQL. The workflow engine we learn about is been redesigned from scratch basically in the past year, and we will see it makes things quite, I think, nice and easy to implement and to use. There is a new plugin infrastructure. So up to now, plugins were there from the very beginning, but you had to put specific Python files in the AiiDA set of files. Now we can develop plugins completely independently in independent repository. You just have to, basically, when you create them, write something specific using pip. But just you have to say, this is a plugin for AiiDA with this name. And then when you install it, AiiDA will find it and use it. So it really allows to push development of plugins independent of what we do in the core. There are a number of new plugins which have been implemented for the scheduler, including LSF, which is the last one, but we have PBS Pros, Lerm, SG, etc. And there are a lot of codes which already have, at various stage of, say, completeness, already have plugins for AiiDA. These are probably non-complete list. If you go on aida.net, there is a page plugins, which tells you the plugin existing, the state, if they're ready or not yet, and how to find them, who's the contact person. So you can go there to get the complete list. And we've also been working a lot to make it easier and easier to install it. It's not super easy because, you know, we have a database to install. You have to have some dependencies, so it might take some time, but we are really trying to make it always easier to do it. And we have spent a lot of time with something which is maybe only indirectly useful for you, which is improving a lot of automated testing. Now, at every commit, about 800 tests run for the different backends. And basically, we are sure every commit we do doesn't break at least the existing functionality, and we add new tests all the time. So this is important for us as developers, but it's important for you because it means the code is more stable also when you use it. And just quickly, what will happen in the next months? We'll release, as I was saying, in a few weeks, 1 or 2 weeks, 090. SQ Alchemy is basically stable. We still have this experimental flag. We are working in these weeks to make the final test, add the final missing test to make sure it's stable. So this will give you this 50%, 50 times speed up I was mentioning before. There are some additional improvements which are a bit technical, so I won't discuss them. But if you want to know, we can tell you what we are doing. We're improving the way you can use multiple profiles in AiiDA. Profile in AiiDA is basically, you can think if you use Git as a repository. So if you have different projects, you can distinguish them in different what we call profiles, and we are making it easier to do. We're working on a new document to decide how to share data even more seamlessly. We want to get to an approach similar to Git push and pull, so you can have multiple copies of your data and maybe work on different computers or with different people. And this is a design document, and we work on it after the summer. We're working on the object store, which will make it even faster to store a lot of files, especially on supercomputers. For instance, here we're working very closely with the Swiss Supercomputer Center, which is providing us such a service. The web interface, which is part of Materials Cloud, will be there by the end of summer. And things which we do all the time is really to optimize and do speed ups, which sometimes maybe require one line change in the code, but requires maybe 2 weeks to test, and then gives you really factors of speed up. And other things we're working with will happen after the summer are the new sharing protocol and hashing on nodes, which is just something which allows you to discover it very quickly if you already have the same node already in the database and avoid to duplicate or run again the same computation more and more. Okay, so very quickly, what was the most important probably, the acknowledgements. These are the people working in the AiiDA team. It's already quite a big team, and these are all people developing the code, but I also have really to mention, thank all the people who have been working on contributions, plugins, etc. And I really hope maybe in a few months also your name might be here. And again, now I'm pretty sure someone will be missing from here. And then we have to thank the funding agencies. So we have Marvel, which is a Swiss project hosted here, but involving, actually this number is not updated, it's almost 40 professors in Switzerland. There is MAX, which is another center, European Center for Exascale, and which are the main funders for the development, if you want, and all the things we happen behind. And for this tutorial, we also have to thank, of course, Psyche, which is putting also some money. And this will allow basically to have all the organization things here. The social dinner is offered, all the coffee breaks are offered. So we really have to thank the sponsors. OK, so let me just conclude very quickly. I won't stop here. It's just the 4 pillars I was mentioning. So AiiDA can automate your calculations, abstracting things into API, and coupling with data, where things are stored in a graph to allow you to automatically have reproducibility and provenance in an environment which makes things easy to use and to allows you to write very complex scientific workflows and then share them to boost research. There are some pointers to some links of the repository, of the website, the Facebook page. And the Facebook page, actually, you will probably see your pictures later in the afternoon or tomorrow. And I think